Fee, fi, how frantically I square my talk. It's probably from Shakespeare, although I'd have to look that one up. Okay, hey, welcome to mini presentation C for the History and Philosophy of Mathematics course at Mayville State University. My name's Jonathan, and I'm presenting on Flatland. Who wrote Flatland, and why are we still talking about it 135 years later? Well, it was published in 1884, and its author was A. Square, a resident and gentleman of Flatland itself. So obviously it wasn't really written by A. Square. In the second edition, Edwin Abbott Abbott identified himself as the author. Who was Abbott, and why did he write such a cool book? Edwin Abbott Abbott was a theologian and schoolmaster. He was the headmaster of the City of London School at the time that he wrote Flatland. Here's a brief synopsis of how the story goes. In the first part of Flatland, we hear from A. Square's perspective. He's the narrator. We hear from his perspective what it's like to live in Flatland. Well, there's triangles and squares and other polygons, and they all live together. Square talks a lot about sight recognition and how they recognize each other. He explains that when he sees another polygon, all he sees is a line, but he can infer from the shading of that line how many sides the other polygon has. And knowing how many sides another polygon has is a big deal because that's the whole basis of their social structure. There's a social order in Flatland. When you're a triangle, you're the lower class. Equilateral is as good as you can get as a triangle. When you're a square, that's better. Pentagons, hexagons, that's pretty high class. You get a lot of polygons, they get big and then they become circles and they're the priests. And in Flatland, Abbott presents us with a satire of his own Victorian England. And I could probably talk for a really long time on the satire of Victorian England, but let's skip ahead to the math part. So in part 2 of the book, it starts off with Square having a vision. He has a dream that he enters Lineland. And eventually the king of Lineland chases him out, and he wakes up in a fright to discover that he's still in Flatland. Later that day, Square is visited by Sphere, who he initially thinks is a circle. And Circle appears right in his living room and changes sizes in a really weird way that confuses Square. And Square is kind of taken aback by this. And he kind of has these arguments with Circle about the nature of dimensions, and Circle tries to convince him of the third dimension, but Square will hear none of it. And they argue, and eventually Sphere picks him up into the third dimension and shows him his house from above and essentially convinces him that in fact there's more to Flatland than Flatland. He goes back to Flatland as a believer in 3 dimensions who, he's imprisoned, of course, because that's how it works in Flatland. When you're mad, you go to prison. So that's the end of it. It's a tragedy. Shakespearean. What was I going to say about Shakespeare? Abbott was well versed in his Shakespeare. He published a Shakespeare's Grammar in 1869, 15 years before he wrote Flatland. His students performed Shakespeare plays every year. Oh, day and night, but this is wondrous strange, is Horatio's perplexed response upon hearing the ghost of Hamlet's father. All in all, Flatland really does represent a science fiction classic. Wikipedia goes on to say that with the event of modern science fiction from the 50s to the present day, Flatland's seen a revival in popularity, especially among science fiction and cyberpunk fans. It's been said that more correctly, Flatland is mathematical fiction rather than science fiction, but either way, it's definitely part of our culture. Pickover writes, today computer graphic projections of 4D objects bring us a step closer to higher dimensional phenomena. So Pickover refers us to Klein bottles and tesseracts in his See Also section. So tesseract is the 4-dimensional analog of the cube, just like the sphere is the 3-dimensional analog of the circle. Much in the way that Sphere went through Square's Flatland and became a circle, a tesseract passing through 3-dimensional space would appear as a cube. The term tesseract was first coined in 1888 by Charles Howard Hinton, and there's a note in the notes of Flatland referencing Hinton as an influence on Abbott. The Klein bottle is a great example for thinking about higher dimensional objects. It's a single-sided surface that's folded back on itself so it can't be constructed in only 3 dimensions. In a true Klein bottle, the intersection where the surfaces pass through one another don't intersect at all. But like the sphere, who gets projected as a circle when he passes through the plane of Flatland, the Klein bottle's intersection is unavoidable when you project it in 3 dimensions. I mentioned Mobius strips, and I didn't mean to imply that they're 4-dimensional objects. Like Klein bottles, they are non-orientable surfaces. In the Mobius strips case, it's a 2-dimensional object that we're able to embed in 3 dimensions. Well, sort of. You have to ignore that it has thickness when you construct one in 3D. Multiple dimensions is an inseparable part of string theory. There are various flavors of string theory, and the number of dimensions needed to get the mathematics to work out nicely is different for each. Superstring theory, for example, requires 10 dimensions, and M theory requires 11. For each, there's the 2 that the square was familiar with, the 3rd that sphere showed to square, a 4th, time. We usually think of time as being the next dimension to enumerate over length, width, and height, hence the term space-time, and then 6 or 7 more. Current thinking is that these extra dimensions are tightly rolled up onto themselves so that they're closed away from the dimensions that we're familiar with. We call this compactification. Similar to how Klein bottle is a 2-dimensional manifold, which we can represent in 4D, the Calabi-Yau manifold spans 6 dimensions. The dimensions of the Calabi-Yau manifold are compacted, rolled up very tightly, and this is similar to how string theorists envision that the higher order dimensions required by the mathematics of the theory might manifest themselves. It doesn't surprise me at all that Pickover chose Flatland to be in this top 250 math picks. It's a delightful story that has withstood the test of time. Thanks for listening. So in their ranking system, the more sides you have, the better you are. But it's also interesting that he talks about the health of the inhabitants of Flatland and has as you have more sides. Oh God, we won't talk about that. Getting way into the health of the Flatlanders. Yeah, right. You only get one shot every 1,000 years. So Sphere really has to work hard to convince Square that in fact there's a 3rd dimension, because Sphere's like, well, I'm gonna wait around for 1,000 years, and then this guy's not even gonna listen to me. So he picks him up and takes him right up out of the 3rd dimension into the 3rd dimension. Blah blah blah. I'm such a babbler.